Very good morning. I'm going to present the topic, a recurrent network technique for energy optimization in 6G networks with dynamic device-to-device communication. My name is Sonia, Aneesh. My department is Electronics and Telecommunication from Thermal Engineering College. To start with the introduction, with the advent of 6G networks, the demand for high speed, low latency, and energy efficient communication system has become a requirement. Number of connected devices has increased exponentially. Traditional cellular networks face significant challenges in meeting the increasing traffic demands while maintaining the energy at the optimum level. So one promising solution which can address this issue is exploring the concept of device-to-device communication, which enables either direct communication between nearby devices, which solely relies on the base station infrastructure. So traditional cellular networks, they often suffer from inefficient resource utilization, which has led to increased energy consumption and network congestion. So managing energy efficiency for and density of high density of connected devices is becoming increasingly complex. Integration of day-to-day communication has offered a viable alternative by allowing devices which are in close proximity to exchange the data directly, which can bypass the base station and hence reduce the overall traffic on the network infrastructure. However, successful implementation of day-to-day communication, it also requires careful consideration of factors such as there is network topology, device mobility, and energy constraints. To start with the literature review, so the literature review highlights importance of day-to-day communication as a crucial component for enhancing the network throughput, capacity, and reducing the network traffic load on the evolved node. Several studies have focused on optimizing energy efficiency in day-to-day communication to promote sustainable smart city development. Integration of green communication techniques into smart city development is essential for achieving energy efficient day-to-day communications. Author Zhao et al. Has utilized recurrent neural networks to predict the traffic pattern, enabling dynamic adjustment of power levels in base station. Another author, Ashwin et al., they have explored the application of recurrent neural network in predicting the user patterns to proactively manage the resource and optimize the energy consumption. Rao et al. Has demonstrated how traffic forecasting can lead to significant energy savings and improved network performance. Utilization of day-to-day can lead to improvement in quality of service performance, which in turn will help in energy optimization. Despite these advancements, the successful implementation of day-to-day communication requires careful consideration of factors such as network topology, device mobility, and energy constraints. Existing methods that we have fall short in dynamically adapting to real-time scenarios or real-time network conditions and efficiently managing the energy consumption. In context of 6G networks, the implementation of intelligent day-to-day communication is envisioned to be a key element which is driven by AI techniques. The literature also suggests that optimizing energy efficiency in day-to-day communication is crucial to enhance the network performance, reduce the energy consumption, and promote sustainable smart city development. An integration of green communication techniques, centralized interference mitigation algorithms, and intelligent day-to-day solutions can contribute to energy optimization in 6G with dynamic device-to-device communication. Our proposed methodology addresses these challenges by continuously evaluating and optimizing the day-to-day configuration, based on real-time network conditions and device energy level. So what does the algorithm do? Is the algorithm iteratively explores different combinations of nodes acting as temporary base stations, evaluating their energy consumption over multiple rounds of communication, and by leveraging this recurrent network's ability to learn from the past iterations, the system can progressively refine the D2D configuration, selecting the most energy efficient arrangement for the recurrent network state. It also involves simulating a 16 network environment with varying number of mobile nodes. Now, these mobile nodes will be randomly assigned initial energy levels and a dynamic position within a defined area, which tries to incorporate a realistic node movement pattern. The recurring neural network algorithm iteratively generates and evaluates the candidate D2DL configurations, continuously updating the best configuration based on the energy consumption metrics. Through extensive simulations and performance evaluations, we aim to demonstrate the efficacy of our method in minimizing energy consumption while maintaining reliable communication in 16 nanometers. Now, figure shows the proposed methodology. Now, this proposed methodology, it is a concept diagram of the proposed methodology, wherein you can see that there are battery nodes. So what does these battery nodes? These define the mobile nodes. So you can see the nodes that we have shown is of different varying battery sizes, showing the different initial capacities, initial energies that the nodes contain. Now they are passed through a recurrent neural network. Also, you can see that there are different node positions that the battery nodes have occupied. And based on the recurrent neural network, the decision will be made whether it needs to go for D2D communication or it needs to go for a direct communication. The simulation setup, we developed a custom simulation environment using MATLAB to develop to model a 6G network. Within the defined area, the area was chosen to be 1000 cross 1000 geographical area. Various network parameters were incorporated, like the number of mobile nodes, base station location, communication range, and the node modeling was done using parameters like initial energy and mobility model. Then energy consumption model. So we defined the communication energy with the formula alpha plus beta into D raised to N. So where alpha is the energy consumed by the transmitter, beta is the energy consumed by the transmit amplifier, and T is the distance between the communicating nodes, and N is the path loss component. So the mobility energy, that is communication energy, was the previous formula. The mobility energy is gamma into V square T. So gamma is the mobility coefficient, and V is the node velocity, and T is the time in motion. Now, we designed the network and implemented a recurrent neural network to optimize the D2D communication configuration by minimizing the energy consumption while maintaining reliable connectivity. So the figure that you can see is the random locations of the nodes which the nodes take once the simulation starts. The different colors shows the different locations that the node takes in a single in iterations. Means each node can take different positions. Okay, so based on the positions, if you can see, they are moving in all the 4 quadrants. The training process involves feeding the recurrent network with simulated network scenarios, including node position, energy level, and communication pattern. Network will learn to predict the most efficient D2D communication based on these data. Then, how do I do the configuration updates? So for the configuration updates, the recurrent network updates this D2D configuration after every simulation steps, 100 simulation steps, considering the current network state, and it will predict the most energy efficient arrangement. We have assessed the effectiveness of the proposed approach using the following metrics: overall network energy consumption, node lifetime, network throughput, and quality of service. Now, for the results and discussions, this is the table that we have prepared for the simulation of various amounts of nodes, wherein the table shows the number of nodes and what is the total energy, network energy for the first iteration. Then at the last iteration, what is the energy left? And what is the last iteration value? Till which iteration does the network run? And what is the time elapsed in these iterations? So, to be more specific about it, so what does this provide? The number of nodes column. It denotes that the count of devices or sensors which had participated in the network. which is ranging from 1 to 9. Larger networks, now if you can see, larger networks tend to exhibit higher initial energy consumption, and which is indicated by the second column, which is the total network energy for the first iteration. Similarly, the network with 9 nodes, if you see, it starts with an energy consumption of 25773 unit, significantly, which indicates higher than the network with only 2 nodes, which is 2315 units of energy. This figure shows the energy of each of the 5 nodes, or each of the five, what you can say, nodes, which is varied over time. The each circle indicates the energy level remaining with that node. Colors which are given to the circle, they are random colors, energy specified in joules and derived from the battery capacity of a typical new generation phones. So you can see this is the energy remaining based on the number of nodes. So it's a plot of remaining energy versus the number of nodes. Now, one significant aspect that we have analyzed was the impact on the node lifetime, which served as a crucial indicator of device sustainability within the network. In our baseline simulation, where D2D communication was absent, nodes exhibited an average lifetime of 17 hours under moderate network traffic conditions. But on implementing D2D communication and applying a recurrent neural network optimization, the average lifetime, it saw a substantial increase to 28 hours, representing a significant improvement of 65%. This extension in battery lifetime holds considerable importance for ensuring the prolonged operation of mobile devices within the 6G networks. Additionally, we evaluated the effect of our optimization technique on overall network energy consumption. So by generating these optimized D2D configurations, we observed a notable 37% reduction in energy consumption in comparison to traditional cellular communication scenarios. These results highlight the significant potential of our recurrent network in optimizing energy consumption for 6G networks with dynamic D2D communication. So by leveraging this recurrent neural network's ability to learn, to adapt and evolve, our approach has continuously refined the D2D configuration, leading to substantial energy savings and extended node lifetime. So one advantage of our technique is the ability to strike a balance between energy efficiency and quality of service requirements. Despite the energy optimization, simulation has demonstrated that our approach maintained acceptable throughput and latency levels, ensuring reliable communication for emerging 6G applications. Sensitivity analysis revealed the robust performance of our recurrent neural network across various network densities and mobility patterns. Even in scenarios which were characterized by high node density, high node mobility, the energy optimization capabilities in those situations remained effective, demonstrating the capability to adapt to dynamic network conditions. So the conclusion is this study introduced a novel recurrent network-based approach for optimizing energy consumption in 6G networks with dynamic D2D communication. So our findings demonstrate significant improvement in energy efficiency and network performance. The proposed technique achieved a 65% increase in average node lifetime and 37% reduction in network energy consumption compared to the traditional cellular communication scenarios. The key strengths of our method lie in the adaptive nature and the ability to balance energy efficiency with quality of service requirements. So by continuously refining the D2D configuration based on real-time network condition, our approach maintains reliable communication while minimizing energy expenditure. However, the study has limitations under some consideration. So the situations were conducted in a controlled environment, which may not fully capture the complexities of real life scenarios. Factors such as environmental interference, hardware variations, and urban landscape intricacies were not accounted for this model. So the key areas for future work include real world testing and refinement of algorithm to enhance its robustness in diverse environment. Integration with other emerging 6G technologies such as AI-driven network management and edge computing, extending the framework to investigate the scalability of the approach for ultra-dense network scenarios. These are the references that I have referred for the presentation as well as the paper. So these are the references. Thank you.